So this is 2024 HSC question number 30. An equilibrium mixture of hydrogen, carbon dioxide, water, and carbon monoxide is in a closed 1 liter container at a fixed temperature as shown. They've given you the KEQ as well, which is 1.6. So in your reading time, you have a bit of an idea of what you're doing. You're calculating K, guys. You're not going to be able to fill out every number in the ICE table. Yeah, so just prepare yourselves for that in reading time. You're probably going to have some X's in there. You have to be solving for some kind of concentration. The initial concentrations are this, 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 and this. From your experience in class, you know that when you're subbing concentrations into the equilibrium expression, you need all of the concentrations all at the same time. So this sentence right after the equation, I'm in reading time, I'm collecting the information, yeah? When they've given me all of these concentrations, that sort of makes me feel like I can sub it into the equilibrium expression. Maybe, just maybe, I'm calculating Q and then comparing it to K. Okay? I'm just collecting information during reading time. I'm definitely not subbing it in to get K because I've already got K. These are initial concentrations. So guys, when I do sub it in, I don't get a letter K. What letter do I get instead? Q, exactly. These are initial concentrations. Just an idea. Let's keep on reading. An unknown amount of CO was added to the same container and the temperature was kept constant. The temperature has to be kept constant because otherwise, can you use this number? No. K changes according to temperature. So if they're going to give you K and they want you to use it, they have to tell you it's the same temperature. After the new equilibrium had been established, the concentration of H2O was found to be 0.2. Using this information, calculate the unknown amount of CO that was added to the container. Okay. So you've been given some initial amounts, you've been given some equilibrium amounts. That's how we know we're setting up an ICE table. So you've got H2G plus CO2G turns into H2OG plus COG. We know we're setting up an ICE table again because they've given us some initial and some equilibrium. That's what I and E stands for. Okay. They've actually given you all of your initial amounts. That was the sentence right underneath the equilibrium, so I can pop that straight in. It was 1.0, it was zero point 0.5, zero point 0.4, and 2.0. And then they also said after the new equilibrium had been established, the concentration of H2O was found to be 0.2. Oh, sorry, H2O, which is this one here. Now, hold on. Does this look like you could fill out every number in the ICE table? Yeah. But we said we're not doing that. Okay. So, guys, when you fill out the ICE table like this, it kind of looks like this. Oh, H2O started at 0.4, it went to 0.2, so then it must be minus 0.2. And then things on the same side have the same signs. This is also minus 0.2. And then the other side must be plus 0.2. So then it kind of looks like you're filling in the ICE table and you've got every single number, which we said you can't because they've already given you a K. Okay. And also they asked you for an amount in the ICE table, which means we're missing something here. What did they ask you for? They asked you for the unknown amount of CO that was added to the container. Okay, so let's call that X. X is the amount of CO added to the container. It has to be in your ICE table. Again, we've established that because otherwise you would just fill every number in and then solve for K, even though they've given you K. So X has to go somewhere in this ICE table. Where, any guesses where you might put X? Yeah. X would go in the initial with the 2.0 for the CO. Can I ask, do you know why?
Because it says the CO was added to the container, so like a new equilibrium will be established after it's added.
Yeah. Yeah, pretty much. When students read this question, they think of they get confused between the change that the system does and the change that we do. Okay. So guys, what I want you to keep in mind is that the initial captures any changes imposed. Let's put it that way. And I'll illustrate it to you better with a graph. Yeah. The initial is, yes, the initial that's already in the container, but the initial row in your ice table also captures any changes imposed by the scientist. Okay, let's put it that way. Now, the C, I know I'm aware that C also stands for change. C captures any gradual changes the system does as it shifts. Okay, so there's a difference between any change that we do and any change that the system does. Anything that we do, that still goes in I. That's the reason why you guys are correct. The amount of CO that you add to the container, that unknown X, goes here. It goes in the initial. What students usually think is they put it here, which doesn't make sense because you should already know what the change is based on the H2O point 4 to point 2. Now, this was easier to figure out that it goes in the I than the C because you already know that it can't be in the C because we had tried to fill it out earlier. The best way of explaining that it goes in I is actually through your graph. Yeah. So let's draw it out. You can feel free to sketch this part if you want to, or just have a look. Let me do it accurately because they actually have given you the numbers. This is time. So point 4 is H2O. This is not to scale, this is just to show you. And then point 0.5 is CO2, and then 1.0 is H2, and then 2.0 is CO. Okay. When you, what did we say when we were drawing the graphs a few lessons ago? We said that any immediate up or down is any change that we impose. Yeah. So if the system, the question told you, oh, they added an unknown amount of X, and we happen to have called that we added an unknown amount of CO, and we happen to have given that the letter X. What that would look like on your graph is this. Okay. And then eventually it goes back to equilibrium, right? Now, guys, remember when we were drawing it? And then we drew the equilibrium, like and it goes, the line becomes flat again, right? Because when you're at equilibrium, the concentration becomes constant again. When we were drawing it, did we say that you connect the line from the old equilibrium or from the top? When we were drawing it before. Yeah, when we were drawing it before, we said if you've put in a vertical line, something like this, you ignore this old point. This is the end of the old equilibrium. Okay. So I want you to keep in mind this straight line from before, this point here is the end of the previous equilibrium. When you do a shoot up or a shoot down in your graph, this point here is the start of your new equilibrium. Okay, so that's why in your ice table, I know they told you, oh, the initial amount is 2, but then in our ice table, we don't fill the initial amount as 2, we fill the initial amount as 2 plus x. That's because the amount, yes, was initially 2, but because you added an x to it, the 2 plus x becomes the start of your new equilibrium. Yeah? So the 2 was the end of the old equilibrium. If you didn't do anything to it, the end of the old equilibrium would be the start of your new equilibrium. But this is the one that you impose the change of. So when you go to connect the lines, you do it from the top here. So the 2 plus x is the start of your new equilibrium. Yeah. So that's why that unknown that we're looking for goes into I and doesn't go into C. C is the change that the system does. Any change that we do goes in I. Okay. So that's pretty much it. You're not supposed to be filling in C for any change that you do. That goes in I. So then we fill out the rest of the ice table the same way. We now know where X is. H2O is 0.4, it went to 0.2, so the change is minus 0.2. Any change on the same side has the same sign, so CO is also minus 0.2. Any change on the other side has the opposite sign, so H2 is plus 0.2, CO2 is plus 0.2. So guys, what's the equilibrium for H2? 1.2. What's the equilibrium for CO2? 0.7. And what's the equilibrium for CO? 1.8 plus x. Exactly. Now that you've got your E row filled out, we can sub it into your equilibrium expression. And then solve for x. So let's move it over here. K is equal to, Advit, what's our equilibrium equation for this? Our equilibrium expression for this equation?
The concentration of H2O multiplied by the concentration of CO over the concentration of CO2 times the concentration of H2.
Yes. And there's no raising to the power of anything because everything's a 1-to-1 ratio. So H2O is 0.2, CO is 1.8 plus X, CO2 is 0.7, and H2 is 1.2. If you have an X, you need to know what your K is. If you fill in every number in your ICE table, you should be able to solve for K. Here we have an X, so we need to be given K, which is 1.6. So we're just rearranging this to get X. So I'm going to do this step by step so no one gets confused, yeah? But I'm aware the maths might be a little bit, I might be going through in a bit too much detail if you're comfortable with it. I'm going to multiply the denominator over. I'm going to divide the 0.2. And then I'm going to subtract the 1.8 to leave the x on its own, okay? Right. What do we get for x? The amount of the concentration of CO added. X came from your ice table, which is concentration. Okay, I'll take the 4.92. This is molar. And that's concentration. But guys, the question wanted amount in mole. So what's our final step? This is concentration of CO added, which means moles added is, yeah, C is N on V, so N is C times V. So 4.92 molar by, however, the volume in the question anyway was 1 liter, so you're just going to end up with the same number. And every number, the smallest sig fig that we used was 3, so we're rounding off to 3, 4.92 mole to 3 sig figs. Okay? All right. So your answer is 4.92. Let's talk a little bit about how you would approach this in the exam though. Yeah. Let's say you have the experience now. You know that if you're adding anything and you're disturbing the equilibrium, that unknown x that you added goes into I. Let's say you were back at your original situation. I'm going to redraw this just so that you have the working out all nice and neat. We're just doing an extra demonstration. What happens if we go back to our initial scenario? and you didn't know where to put X, or let's say you even forgot that you were supposed to put in an X, yeah? Because once you started to fill out the ice table, you would have realized that you had everything you need to fill out the ice table, and then you might have completely forgotten about X. Okay? So if you did this and you forgot there was an X here, it kind of looks like you can fill in the ice table. So it would have been minus 0.2, minus 0.2, plus 0.2, plus 0.2, 1.2, 0.7, 1.8. You would have ended up at a situation like this, okay? If this was correct, okay? So if you have time in an exam, you're allowed to experiment with what you think is correct. You just aren't, what you aren't allowed to do, or what you shouldn't do, is once you realize that something's wrong, keep on going. Yeah. So let's say you did this and you didn't yet realize that it was wrong. Okay. Let's say we forgot there was supposed to be an X. Once you got to this point, what would you have kept on doing? Like you filled out your E, what do we normally do after? You sub it into the equilibrium expression. So let's try. And then guys, did they give you the equilibrium constant for this question? They did. So if you were doing this correctly, you forgot the X, okay, and you still thought you were doing this correctly, when you sub this in, it should equal what? What was the K in the question? 1.6, okay? If you were doing this in the exam and you were continuing to experiment with what you thought was correct, you would have subbed this in, and then you should get 1.6, just like the question told you. What do you actually get though, guys, when you do this? 0.4285. Okay, so I just want to let you know that if you're doing a difficult question in the exam, it's okay to experiment with it. You just need to keep an open mind about what you actually have going on in the question. Yeah. So it would have been fine. Like you're allowed to do this. Just cross it out after once you realize it's wrong. But you're not going to realize that this is wrong because it looks like your standard question. What you need to be doing when you go into your exams is if you feel like you're done with the question, please just go back and read what the question asked you for to make sure that you give the marker what they wanted. Yeah. Because if you blindly went into the exam with this, you would have been like, I finished it, I got K, and then you would have flipped over to your next thing. Yeah. If you were doing it right, then you should have gotten the same 1.6. When you realize you don't get the same 1.6, that's your signal to go back to your ice table and realize that there's something missing. Yeah. So that's how you would have ended up here when there's no one else in the exam, when there's no one else with you to let you know that there's supposed to be an X somewhere. Okay.